So it's 3 o'clock. It's the first Wednesday in the month, and welcome for our monthly color management cafe. This is an extraordinary cafe just for two reasons. One, we have it in English language for good reasons, and the second reason is our guest speaker today, which happens to be Professor Mark Fairchild, who will update us today with recent highlights from the monthly color science lab at RIT. Again, we record that cafe, and we highly encourage you to discuss, to ask questions. You can raise your hand, and then I unmute you, and then you can ask orally, or you can simply write down your questions, and we try to read the question then and give Mark the chance to respond on it. And as always, so to speak. And before he will start, let me give you a very brief introduction. We will just have a few words about RIT and the Color Science Lab from my little viewpoint. And then, of course, for the approximately 90 minutes, we will have Mark then being on the stage. RIT and Fogra. Maybe you remember this person here on the left. I had the privilege to be a student there both in 2004 and 2007 with my friend Justin here on the right-hand side. He's now with Apple. And I forgot the name in the middle. It's Yonga, I expect. Maybe, Mark, you remember. And based on that time, we did some collaborations. You see on the left, I helped Dave Weibel to translate the original basic paper from Neugebauer, which was only present up to that time in German language. And again, small bits and pieces around the color science food chain. For me, it was a very cool and informative time, which I would not miss anymore. And with that in mind, we just meet ourselves at different events, and I'm very glad and very happy to have you here, Mark. And you can show your webcam now, and I would like to make you presenter, and also, of course, asking you to introduce yourself and the lab.
Okay, thank you, Andy. All right, looks like the screen sharing properly. So thank you everyone for joining us today, and thank you for holding the meeting in English. I would not do well at all in German. It would be a very, very, very short presentation. So thank you for accommodating my native language. So what I'm going to do today is Andy's given me a few topics to discuss, and I'm going to sort of weave that into some recent topics of research that we've done in the lab, and try to pause every once in a while for some questions if you have them, because the topics jump around a little bit. So I'll take little breaks as I change topics. But feel free to interrupt at any time. The way my setup is here, it's kind of hard for me to notice, but I've already told Andy if somebody raises their hand or puts something in the chat, he can speak up and interrupt me, and that's fine. Just to introduce myself in the lab a little bit, I have a few slides here, and I'm going to go back to a demo in a second, but I come from a place called the Rochester Institute of Technology, which is a university in Rochester, New York, in the U.S. And we have a program of color science, which is a graduate program, master's and PhD degrees dedicated to color science. And we're also in a laboratory that's called the Munsell Color Science Laboratory. And I have a couple slides in a moment that will explain where that name came from. But I'll just mention for now that we're not directly associated with Munsell products or with X-Ray, who owns the Munsell color products at this time. So most of my recent research has been looking at individual differences in color perception, color matching, color appearance, and so on, and the impact of that on how we perceive images. So that'll be the general theme. I always start with a slide about why is color. So, and Andy asked me to do that, so I will do that today, but I have a few other things first.
And if you want to start me the poll, just let me know. I can just start the poll on requests.
Okay, yeah, I have a slide that'll say when. The first one comes up pretty quick.
Perfect.
So yeah, we have a couple polls we set up to let you all answer some questions for us. So how this day started is I was working with my student here. So this is a picture of me outside our lab at RIT. This is my student on the left, Haoji. And we've been studying brightness and chromaticness and colorfulness and saturation. And it turns out that I'll say old German system, the Dean system of color order, is set up to sample color space in a way that's very interesting and useful for our research. The basic idea is that these columns in the system that I'm holding, the page that I'm holding, which is an orange hue, they're all constant chromaticity, which is constant perceived saturation. And the idea of the system is to have equal increments in saturation. And all these rows are not constant luminance in this system. They're actually designed to be constant, what's called darkness in the Dean system, but we would call it lightness normally, which is actually part of what we're studying, the fact that luminance and brightness aren't the same thing. So in my search for a physical system, which we didn't have in the lab, I tracked down one that was for sale, and it turns out it really wasn't for sale. And then I thought, well, I'm going to start asking some of my friends in Germany if they have one sitting on a shelf somewhere. And I contacted Andy, and he said he would search, and he found one that got sent to us. So I promised a picture of us holding it at the lab when we received it, which was a couple weeks ago. And what Andy asked in return was that I give a seminar, which I'm happy to do. You didn't have to give me a color system to get me to do this. I would have done it anyway. So that's a little.
I come back to that. Don't promise too much.
But I got the system, and it's being used in our research actually today. We use it to teach people what saturation looks like before we have them do a visual experiment. So another thing Andy sent me was this image that he saw online. I don't know if it was sent to him or how he got it. And he said, this is the kind of thing we struggle to explain. And if you can read the text that went with this image, the crazy thing is there are no red pixels in the image. Your brain added them. So the Coke can appears reddish, and the assertion here is that there are no red pixels. And that says to zoom in, and I can do that. I'm going to get out of my presentation mode here. And I can make this bigger if I want to, but I'm going to do it a slightly different way. I'm going to go to my little color meter, which lets me sample colors, and you get a little zoom in this screen over here. So if we go and look, you'll see that the image is made up of essentially bright and dark lines. There are some different colors in there for the bright lines. There's sort of neutral ones. There's sort of cyan ones. There's some greenish yellow ones up here, and so on. But there's no individual pixel that we would call red. I would argue there's plenty of red information, because if you look up here at the RGB values, if you can see them on your screen, they are changing, and they're changing in what I'd say uncorrelated ways. It's not a monochromatic image. So it is an interesting visual illusion in that there's no pixels we would call red. We recognize a Coke can is usually a red object, and it's easy to perceive that. And Andy said, what's going on here? And I said, oh, this one's easy. If you think about the way the visual system perceives color, that one of the first things we do is we adapt, our brains adapt to kind of a spatially blurred version of the image. So all I did was I blurred it, and then I white balanced it. So I clicked on the Coca-Cola text, which is white, to make that neutral again instead of cyan. And what I got was these images here. So here's the original again. Here's a blurred and white balanced version. And now there are red pixels. And it just turns out I exposed them. So you can see here the can is 180, 127, 128 for RGB. It actually is reddish once you white balance the image and blur it a little bit, which I don't want to imply that this is what you see when you look at this. You certainly can see the spatial configuration, but this is a representation of what your brain is processing in order to give you the final interpretation. So since your brain blurs it and does a little averaging, does some what we call chromatic adaptation that I'll demonstrate later, it's getting that red information, even though in a literal sense, in a physical sense, it's not sitting there in the image. So that one was actually a fairly easy one to explain in terms of the visual models that we work on. So let me go back to my slides here. And I just like to start with a demo like that to get you thinking about visual perception and the types of things that we try to model when we're doing color science research and trying to understand what our brains are doing, what our eyes and brains are doing in order to derive mathematics that can predict it. So here's the first poll, Andy. And I guess he can bring that up for you and you can answer.
Just go on, just keep on talking.
So the question, is there color without a human observer? And I think you're only allowed to give one answer. So pick your favorite answer, yes, no, or maybe. And I'll keep going on here, and Andy can let me know when he's got the answers.
We are collecting. We have 44% voted now, 53, 54. So we normally wait to 70%, 75% of people voting. So 66. So normally, let's get to 70%. Come on. 73%. So we can close the poll. Let me close. Yeah, maybe get more. 73. People need to be woken up. Okay, we close it and okay. And this is, do you see the results, Mark?
I can see them on a small screen here.
That is, yeah. 42% yes, 50% no, and 8% maybe.
Okay, so roughly half and half between yes and no, and some people hedging their bets with maybe. And this is a question, you know, we could go to a pub and have a beer and talk about it for a while, and it's somewhat of a philosophical question. For me, the answer is absolutely no, because that's how I define color as a color scientist, and that's actually how the CIE defines color, is as an attribute of visual perception. And we can talk about the stimulus that we have. In fact, I'll go to the next slide. I gotta get back there, okay. Which is the slide I use for describing why color happens. We can describe the stimulus with physics and chemistry and, you know, do measurements, and that's completely separate from the human observer. So that's one way you could answer yes to that question and it be a valid answer. There's measurements you can do on the object separate from the observer and know something about the stimulus. But I would argue you don't really know the color until somebody's perceiving that in some environment, because the environment can change that color appearance. I'll show a couple demos later on. So when we talk about color science overall, we talk about this triangle here where we have the light source at the top, and we describe that with physics. We can measure the amount of energy wavelength by wavelength in the spectrum. We have materials, they could be prints. In this case, they're color markers that a child would play with over here, and then we have an observer. And I did put human observer in there. We could argue whether animals have color vision. They don't describe it the same way we do. Probably they see, some animals see color in a similar way. So the human might have been part that threw you a little bit on answering that question. But what goes on here is we have the physics to describe the light, the physics and chemistry to describe the interaction of objects with the light. That light reaches the observer's eyes, and then her eyes detect it, her brain processes that, and she perceives the color. So I would argue we need all three to really have color overall. And you'll notice the triangle also has an interaction this way, that the observer interprets the lighting and looks at it for one thing, but also interprets it cognitively, and that impacts the appearance of these objects. That's part of how we adapt to the scene. In a sense, that Coke can demonstration, the fact that our perception is different from what we physically would have measured. If we just measured those light and dark bars, we never would have measured anything that we thought was red. but our perception did some different processing on that and produced that red appearance. So we get into the anatomy and the physiology and the psychology of the observers and the whole interaction of that process is how we define color science, very multidisciplinary. So I pulled a few slides from an overview that we give the freshman students here at RIT, and I'll just jump into that. Again, just so you notice, same slide as my first slide in the overview I give the students. So I'll skip over that one and mention Albert Munsell. So Munsell was an artist and an art teacher, and he died in 1918. So he lived over 100 years ago. And in 1905, he published a system called the Munsell Atlas of Colors, what's come to be known as the Munsell Book of Color. And I'll skip ahead because I have some pictures of some historical versions. But basically, as an art teacher, he was frustrated that he couldn't communicate color precisely. So he developed this system based on hue, which these different pages are different hues, lightness, so along the vertical axis of a page here from the book, these pages over here, we have lightness, which he called value, from black to white. And then chroma was his third dimension, where neutral colors have very low chroma. Out here on the right side of this particular page, they're very high chroma. So he chose those three dimensions. He scaled them to be perceptually uniform within each one. So each step in value was intended to be an equal perceptual step in perceived lightness. Value 5, which is halfway between 0 and 10, should look like a middle gray, and so on. So that's the system. It's still available today. You can still purchase a Munsell Book of Color. Other products like the X-ray color checker chart that's very common in imaging, or at least it's commonly seen, was a Munsell product. It's specified with Munsell colors and Munsell papers. So that's who we're named after. The reason why is because after his death, his family basically took over the company and they created a foundation to run the company in his absence. And when the company was sold, that foundation existed to support students to study color science at various universities around the world. What they did in 1983 was they actually voted to dissolve the foundation, transferred all the assets to RIT, and endowed our laboratory. So they decided the best thing they could do with their foundation money was create a lab that honored Munsell, and it was named after him. So that's where our name comes from. And our objectives are to provide education, applied and fundamental research, measurement, which was a big deal back in the 1980s. We were able to do measurements that a lot of people in industry couldn't do, so we would do them as a service. We don't do that so much anymore because the instruments are very common and inexpensive now. And the collaboration. We work with other companies, universities, government, and so on to do our research and education. So that's where we came from. That's why we have the name Munsell. Our group right now has 6 faculty. The names are here. You might recognize some of them. Is joining us from Norway in January. She'll be coming in just a few weeks. And Chris Thorstensen just joined us this past fall. So here's 2 of them, Mike Murdoch, who you might have seen, and Susan Farnand. And these are a couple, actually recent graduates now. They were students when the picture was taken. Ben Bodner, who finished a master's degree, and Fu Zhang, who finished his PhD in the past year. They're both working at Apple now, coincidentally. So a sense of the size, we have 5 or 6 faculty. We have about 20 graduate students at a time. Almost all of them are in our color science master's or PhD program, but occasionally from other programs around the campus. About 130, 140 alumni around the world. And we've published lots of papers. That's what we're about. We're about doing research and sharing it. So here's a nice little picture of one of our students finished her PhD dissertation and graduated. So we had a little reception in the lab to honor her. So you can get a sense of sort of the size of the group there. It's a nice small group that enjoys studying and researching color science. Just very quickly, these are the courses that we teach in the program. So principles, basic colorimetry, computing and psychophysics. We study the history of research in color science, Color physics is how we model systems and measure them. Modeling visual perception is the course I teach, which is basically color appearance modeling, and then more research and publication seminar where they learn how to write proposals and things like that. They fill it out with elective courses, and then they do either a thesis at the MS level or what we call a dissertation at the PhD level, which is a more longer term research project. And just to wrap up that overview, we had our alumni provide answers or finish the sentence. I started the sentence, color science is ... and then I had all of our alumni send in answers. And this was one that I like in particular, where the response was multidisciplinary, basic sciences and technology used to understand and improve what you see. And that's a good summary of sort of the philosophy of what our lab does. So if you're ever in Rochester or come out of your way to come to Rochester, feel free to contact us and visit the lab. We'd be happy to show you around. So let's jump into some of the research questions. Checking my watch here. So 2 big color questions, and I'll go quickly through the questions. The big question is, what do you see? When you look at a stimulus out in the world, what do you see? And that's the basic question of colorimetry and color appearance, right? We want to be able to measure that stimulus out in the world and maybe reproduce it on a print or on a display, or maybe just understand what the person's perceiving. And as I mentioned, most of my research recently has been focused a little bit more on the individual differences, which is the question, do you see the same thing that I see? So I illustrate 2 pictures of the same field here, not to say our color vision is this different, but just to say that there are differences and they can be quantified and understood, and I'll give you some examples of those. So we start with the color matching functions, which you've probably seen in one form or another. These 2 plotted here happen to be the CIE 1931 and CIE 1964 standard observers, very commonly used, called XYZ, and these functions are called X bar, Y bar, and Z bar. The 1931 functions are for a 2-degree visual field, so sometimes they're called a 2-degree observer. And just as a reference, if you hold your thumb out at arm's length, I'm covering my webcam with my thumb basically, but it's at arm's length. The width of my thumbnail is about 1 degree. The moon or the sun in the sky is about ½ degree for reference. So the visual field for those 1931 experiments was 2 degrees wide. And the reason for that is that's where our best color vision is, in the central fovea, in that part of our visual system where we look at things when we want to read them. So if I say, I want you to read this word wavelength over here, then you move your eyes in your head so that the letters of that word fall on your central vision and you can read them. If I say, look at the word colorimetry at the top, you do the same thing. But if I say fixate where my pointer is up here on the O and try to read the word wavelength at the bottom of the screen, you probably can't do that because out in the periphery, your vision is not as good. You don't have as good a resolution. So those were the first set of color matching functions where the best vision is. The second set were a larger visual field, 10 degrees wide, and actually excluding the central 2 degrees. And the reason for that is we have this yellow protective filter over our central vision. It's called the macula. That's not critical for right now, but that filter protects our most sensitive area where we have the best visual acuity, mainly from short wavelength light and ultraviolet radiation. So if we happen to glance at the sun, those retinal cells, those cones, the photoreceptors don't get damaged because they have that protection. And what that does is it's like viewing the world through a yellow filter. It'd be like putting on a yellow pair of sunglasses that's absorbing short wavelengths. And it turns out the colors that match in that central visual field don't match in the periphery and vice versa. So when we try to do an experiment with a bigger field, the observers have to choose, does it match out here, this 10 degree wide area, or does it match inside? So they excluded the inside. And they felt this was important for some industrial applications that required looking at larger stimuli, like painted walls, or you could, big sheets of paper, things like that. And you can see the color matching functions are a little different. The dotted ones are the 10 degree observer. And a good way to think of that, these are both averages. They're averages over a population of observers. None of us probably have exactly those functions. And you could think of them as being 2 different people. So the difference between my color matching functions and say Andy's color matching functions for even a 2-degree field might be just as different as these two. So that's one way they're used once in a while to say, well, they match for the 2-degree observer, but they mismatch for the 10-degree observer, and that gives you an idea of how big the individual differences could be for that particular metameric match. So that's our starting point. When we want to look at individuals, we have to look at those type of data for individuals. So this plot, it comes from Wachowski and Stiles' color science book, shows the individual observers that went into the 10-degree observer. So Stiles and Birch, 1959. There's 49 observers, they were 10-degree field. And this is commonly used to say, look how different people are. And I like to point out when I show this plot, yes, people are quite different in their color matching functions, but this plot actually minimizes that difference because they were normalized at the 3 points of the primaries that they used, assuming the observers were perfect at those wavelengths. Observers are never perfect. So the fact that the functions go through 1 and 0 at these particular wavelengths actually serves to normalize the functions and remove some of the variability. But it's still quite significant. Over here is the same data plotted as a chromaticity diagram. The red, green, and blue points are where the primaries are. Every set of functions goes through those points, and then you see the spread out here. That doesn't mean there's really no spread between green and red, but the spread falls along a line. And since it's going back and forth along the line, you can't really see it in this particular representation. You can see it over in this one. So just an illustration that there are significant differences between people. This is the end result of some research we did back in the 1990s, where we had people matching a CRT display with a photographic print that was illuminated by fluorescent daylight simulator. So it was a very metameric match. It was projected into a split field. We had different colors on the print, and people would make a match on the CRT, and we would measure the result spectroradiometrically. This is for a cyan sample, so it's basically the cyan photographic primary, maybe a little bit desaturated. And the point I want to make is all these points, there were 20 observers. These are the matches that 20 different people made on a delta plot. So this is delta A star, B star. And the only point I want to make here is the size of the scale. This is plus and minus 10 C-lab units. So what looked like a match to one observer could look like a mismatch to another observer by up to a delta E of about 20. And that's very realistic for that level of metamerism. So this is real data. Later on, probably about a decade later, we did some simulations where we created thousands of sets of color matching functions. And these points are our computer simulation repeating that old experiment. And basically, we got the same results, which is what I want to illustrate for now without going into too many details because we have a much better technique now. So I'm going to skip ahead to the better technique. So the point again here is we started to learn enough about the physiology of the visual system that we could model those individual color matching functions. If I go back a slide, we could say, I can learn something about these 49 observers and try to predict what their functions would be based on their physiology. And we did that by simulation for thousands of observers, and we could simulate the results we see in the real world. So taking a step back, if we go back to 2006, the CIE published this technique. The publication's called Fundamental Chromaticity Diagram with Physiological Axes, which is kind of a obtuse title, but what it is about is saying, can I predict those color matching functions for average observers of various ages and various field sizes? So instead of 2 and 10-degree observers at an average age, which works out to be around 32 years, just by coincidence, can I put those in as variables and predict the functions? And they did a very nice job. I highly recommend this technique. We've used it in a number of applications. And this is their equation. And I don't want to get bogged down in the details of the equation, but I want to show what it depends on. So the L bar, M bar, and S bar, think of those as like X bar, Y bar, Z bar. We use LMS because that represents the long, middle, and short wavelength response of the visual system. It's a little more fundamental metric. It's what the eyes are, how they're actually responding. That depends on the light absorbed by the cones, that's this alpha, so the cone absorptivity spectra. Turns out those depend on field size. So in the fovea, they're different than they are in the periphery. And the main reason for that is the shapes of the cones change. So there's a difference in the pigment density and the amount of pigment that the light goes through before it's absorbed. Then we have a transmittance term. These are expressed in density, so 10 to the minus density is transmittance. So we multiply those by the transmittance of two things. One being the macula, which is that yellow filter that I talked about. That depends on field size. There's a lot of it in the center and none of it in the periphery. And the other one being the rest of the ocular media, which is mainly the lens and the cornea that focus the light on the back of your eye so that you can see sharp images. And that depends mostly on age. So all these variables that go into figuring out those color matching functions depend on mainly two things: how big the field is, the field of view, and how old the observer is. So you can plug those in and you can get color matching functions. This just illustrates a few of them. Details not important here, but these are the 1931 observer and then a 2 degree at age 25 and 65. And you can see there's some shifts, and these are the 10 degrees at those two ages. Again, don't worry about the details, but you start to see differences on a similar order of magnitude as the difference between the 1931 and the 1964 standard observers. The drawback of this technique for me, for my personal interest, is that this is not referring to individuals. What that technique does, and it does it extremely well, so don't take this as me saying it's a bad technique. It's a great technique, and what it does well is it predicts the average of the population for a given age and field size. So this is my picture of a crowd at an old Rolling Stones concert, and just to represent a population. We can predict the average color matching functions pretty well now. But what I want to know is, how does this guy vary from this guy over here? And there's more variation in that than what's represented by the CIE technique. So what we've done is, another student of mine took that technique where I showed you the cyan predictions, the scatter of 1,000 observers, combined it with the CIE 2006 averages. And we say Monte Carlo. I didn't talk about the Monte Carlo simulation, but that's basically randomly building individuals. We randomly take cone responses, we randomly take a lens, and randomly take a macula density, as if we're randomly picking an observer from a crowd, and build those color matching functions. So that's what we've done. And this is more recent work by Yuta Asano. Yuta is one of our graduates. He's right over here. If you happen to know Ronnie Luo, this is him looking at one of our demonstrations at a color and imaging conference. And what Yuta was showing here was a device that we called an observer calibrator. Basically, it made very metameric color matches. And at the conference, what we demonstrated is having one observer make a match. And I think I had just made a match here. And then Ronnie came up behind me and started laughing at my match because it looked like such a strong mismatch for him. And the whole system was designed to really tap into the differences in observers and accentuate them. And the demo is wonderful because, you know, everybody's different, and it really accentuated those differences. So what Yuta did is he started with those mean observers, perturbed those with individual physiological variations in those components of vision that we know about to create individual color matching functions. And this is just one example. Remember those Stiles and Birch results from 1959. This is his prediction of those data. So the gray lines are what his model predicted for those 49 observers, and then the shaded area is the range from the actual data. And they line up pretty well. So we were pretty comfortable that we could predict the variability that's seen in typical observers. We've done a number of experiments and applications of this sense that show it works pretty well. And just quickly, there's a paper. Anybody listening, feel free to email me later on. I can give you the email at the end. I don't know if I put it in a slide. Well, actually, it's right there, mark.fairchild@rat.edu. If you have questions on any of these references. This was a paper in PLOS One, which is publicly available. It's open access. So if you just Google this title.
He was actually at Fogra, and we did some of the tests here at Fogra, and we created We created color 72 color matching functions, and I can later show on our webpage where you can find them. So you can all of our observers here have been individually characterized with this technique. So there's also already some another point where we collaborated in that.
Great. I had forgotten about that when he was over in Europe. That's great. So that's a good reference.
Yeah.
Take a look at that if you're interested. I'll show a little bit of what we do with it. The observer calibrator basically would take LEDs, and this is one example of a match where one was a white LED or a neutral, which is actually this spectrum, which has a big peak at 400 nanometers, but we don't see that light very well, so it still looks pretty neutral. And then these red, green, blue primary, which aren't really red, green, blue, kind of an orangish red, a bluish green, and a greenish blue. And those really hit the points where people are most different. And when you adjust these red, green, blues to match that, what I match would be very different from what you match. So we can really measure the individual differences and figure out those color matching functions. And that's the type of experiment that Andy's referring to. If we do several of these matches, we can then use the model that's in the 2016 paper to figure out color matching functions for an individual. The other thing we can do with it is we can actually make confidence intervals on matches. And I really don't have time today to go into the technique, but it was published in 1961, the technique. It's just that the data weren't available. And since we have the data now to simulate populations of observers, we can figure out mean and covariance color matching functions that allow us to predict the range of mismatches for a given metameric pair in the population, which is potentially a very useful thing to do. I'll leave it at that for now. And then another approach, and this is a more recent paper, same author, Yuta Asano. And this was actually a chapter of his dissertation that we never published. And I kept giving it to students and saying, you have to do what's in here. And we realized we should just publish that chapter. So it just got published last year, where he came up with categories of observers. So rather than doing the careful measurements that you need to do to characterize an individual's color matching functions, we thought maybe if we make something like 10 categories and we can fit people into their best category, that'll be good enough. And we think it really is good enough because there's a lot of variability in making those measurements on any given individual. So that paper is out there in Color Research and Application. And just what you can see is what he did is category 1 is the CIE 2006 observer. This happens to be one at age 38. You could put in a different age if you wanted. But at the field size, that's his mean. All of his other parameters are set to 0. So these are changes in the lens, the macula, the density of the photoreceptors, and wavelength shifts in the photoreceptors. And then the other people, the other 10 categories are represented by people that are different ages, different pigment densities, and so on. And what you get is this plot up in the top where there's 10 categorical observers, 10 different color matching functions. This particular plot compares it with earlier work by Sarkar where they had a different set of categories. It was derived differently, but it's similar, and we want to give credit to that initial idea there. So the fun thing with the categories is you can make an observer calibrator a little easier. It's an easier process to do the experiment. And we actually built this in the lab, not as an observer calibrator. It's actually a light booth. So this is right next to where Andy was standing in the picture that he showed. We used to have a traditional Macbeth booth there, and now we've built one ourselves. And the illumination are 2 theatrical LED illumination systems. There's 7 channels. So we have 7 different spectra we can project into these diffusers, and then there's more diffusers here, which makes a nice diffusely illuminated and very bright viewing booth, and it's divided. So we have 2 illuminators, 2 sides of the booth. We can put different spectra on each side. And then what we can do is put a little prism in front. So and this is actually a photograph. One side of the prism is viewing one side of the booth. The other side is viewing the other side of the booth. And we can make metameric matches. Because we have 7 channels, we can make, for example, the chromaticity of D65 2 different ways. And we can make them match for, say, the CIE 2-degree observer, and then have somebody look at it and judge whether it matches for them or not. Usually the answer is not, because most people are different from the 2-degree observer. So what we can do with this, combined with the previous slide, the 10 categories, is we can go to the booth and say, let's make a match to, say, let's make our best D65 spectrally on the left side, and then on the right side, we'll pick 3 of the LED primaries and make a match for each of those 10 observers. And when we make those 10 matches, we can have people cycle through them, and they'll see 10 different matches, and they'll say, well, that doesn't match, but maybe one of them will. Or maybe they can rank order their matches. I'll illustrate some of those in just a second and figure out which category is best for them. Now, this is all work in progress, so it's not something we do every day yet. It hasn't been thoroughly tested, but we're pretty confident that this will work quite well. And here's an example. So a lot going on here, but I'm going to summarize very briefly. The dashed line in this plot is D65, the actual standard. The larger dashes that I'm tracing out here are the best spectral match to D65 we can make in that system. And then these other 2 are, there's actually 3 wavelengths or 3 LEDs in there. Those are matches to that D65 spectrum for each of the 10 categorical observers. So there's 10 different matches in there. And this illustrates what they look like, and I'm gonna zoom in on that. So we have 10 different stimulus pairs because we've made matches for 10 different observers. And this is the prediction from the CIE observer. I believe this was the 10-degree, yeah, the 10-degree observer. So pair number 1 is pretty close for the CIE observer. If we go down here to pair number 10, not so close. One looks green and one still looks neutral. If we look at our 10 categories, the ones on the diagonal are matches for each of the observers. So that's why they're bold. So they match. That's how they were calculated. And you can see for observer 1, which actually isn't too far away from the CIE observer, you get kind of similar results. The first one is best. Some of them are bad. Others might be close. Number 5 is not too bad, for example. Observer 2, this one's the best. Most of the other ones are green on the right side. Observer 3, number 3 is the best, and most of them are pink on the other side, except this one is green, and so on. So the idea is if you're similar to observer 10, which happens to be our old observer, then you would look at these 10 pairs and say, you know, the only one that's close to matching is number 10. The rest of them look really off, and the right side is pink. And you can do that fairly reliably. So what we do is we ask the observers to rank order those, and then we fit them into the category that matches their rank the best, as a sort of quick way to do the experiment that Andy mentioned that was done at Fogra several years ago. So you rank your 10 choices, you figure out which of these are closest to your color matching functions. That has the promise, you know, this is still somewhat research, to have a more effective form of individualized color imagery someday. How applicable that is depends on what you're doing with it. In some cases, you don't want an individual's match, you want the average match, and that's a good thing. Other cases, an individual match might be useful. And just to illustrate another point, here's another set where, again, we have the best match to D65. It's kind of dashed in here. You can't see it so well. And then we have the least metameric matches for each of the observers. And what you can see is if you design your spectra so they're less metameric, they match at more wavelengths basically, then these matches can be quite good for all of the observers. And I like to include this one as opposed to this, this one. This is the worst case. And it does happen with some displays, like these new displays with very wide color gamuts, that you can get some pretty large differences. But if you're careful about how you design your stimuli, you can make the matches quite good for a wide range of observers. And the basic idea here is really basic colorimetry, that the closer the spectra are to matching, the better the match will be for all observers. The observers don't matter if the 2 stimuli match wavelength by wavelength. All right, so I'm going to take a pause there.
This is something which we also found here in our research, and I just added the slide with Jutta. And the question is, what do we do with those individual? Just imagine I have a CMF for my left and right eye, or for both of them, because even that can differ, or with and without glasses, that can also differ. So we have 4 color matching functions per person, per age. Just in theory, but what would be a use case where we can say that is something we do colorimetry, we do matches for in our typical workflows. The designer has an expression, and you as a print service provider has to produce the sourcing and production and match that somehow.
Yeah.
Besides then, it's going to be complicated and complex. Do you envision some use cases or some ideas? Because when I already think about communicating LAB, where say, oh, white backing, black backing, D6510, D52, people are confused. And if I then also come up with, oh, this is LAB Andy and this is LAB Mark, is there already some idea and how to resolve that? Yeah.
Yeah, it's a great question. And the answer is probably that in a lot of cases, this wouldn't be helpful directly in that application, where you'd say, I'm going to have, if you're making prints to match a display, then of what value is a print that matches for Mark or Andy? It might be very valuable for me, but it may not be the best print for a population of customers. So if I was the only customer, that would be an application. Maybe if I'm making fine art prints of my photographs that I'm viewing on a high dynamic range display, it could be useful to calibrate that system for just me. The one application where people seem to think they could use this in a practical sense is in motion pictures, where they're looking at the
different monitors.
Different monitors, different types of displays, and they're willing to calibrate that system for the colorist that's working on the film. And they want it to be just right for him. And then if the director or the producer, somebody comes in, they're willing to flip a switch and make it match for them as well. And then ultimately the result's got to be the best one for the population. And I think that's where the real application comes in. It's not so much in having everybody have their own color matching functions, but in knowing the range. So I'm going to skip back here. I'm sorry to do this to everybody. But this idea here where you can say, well, for a given display and print system, how big are the differences going to be for a normal population of observers? That could be useful information to have, because maybe you can change the display, or maybe you can change the printing inks or something and minimize that difference if that's important. So I think that's where it has the most practical application, as opposed to all of us walking around with our color matching functions.
And we are, to be honest, kind of lucky here to not have that metameric beast so popular right now. This is maybe coming with HDR, white gumwood things, but as long as you just have one and not two of them, it's still easier than with our print world. Yeah.
Absolutely, absolutely. So this is definitely still somewhat future looking. One interesting application that if you had let's say a movie theater with laser primaries, so you have red, green, and blue at a single wavelength, and there actually are systems like this, and there's a Dolby system that uses 6 lasers to give red, green, and blue for the left eye, and a slightly different red, green, and blue for the right eye, so they can get stereo. But what you could do, and then you wear goggles that let one set of primaries or glasses that let one set of primaries or the other through to give you the stereo. What you could do with that, which is kind of interesting, is the monochromatic primaries are the worst case for individual differences. They really accentuate the differences between people. So the directors of photography and so on of the movies are concerned that, well, people will go in and they won't see the colors I wanted them to see. If everybody had a category, and I'm not saying this is really practical, this is kind of a thought experiment,
Yeah,
but if we all knew what category we were, we could walk into the theater and grab a pair of glasses that adjusted the RGB primaries to us.
Cool. Yeah. Cool. It's like you go in the cinema and then you have your categories when you queue up, category observer category 1. And then that's cool.
Exactly.
Okay. We have 45 minutes to go. Let's go on. We have a few comments here, but mostly comments. People would like to tell you a no, and other people just share something. I just answer publicly so people can have a look at, but there's no direct question so far. So just go on, Mark, please. Yeah.
Okay. Thanks. So everything I talked about so far is in the first step of the visual system, where we're absorbing the light in our photoreceptors in our eye. And that's just saying how much light do the 3 photoreceptors types absorb, and if it's equal, the colors match. If it's not equal, they don't match. The next step, remember back to the picture of the girl with the light and the markers and then her visual system, is that interaction with the illumination. And we refer to part of that as chromatic adaptation, how we adjust to the environment. I'm going to do a quick demo here. I know some of you have probably seen it, but I'm going to do it anyway. So this is just an image of a bowl of fruit. And what I'm going to do is digitally, I'm going to cut out a cyan filter and place it over just the banana in this image. So the banana is essentially red light and green light from your display, and very little or no blue light. My cyan filter, which looks like this, is absorbing the red light, transmitting the blue and green, assuming I actually put a filter over a display, which I'm only doing computationally. So if I go back to my banana, it's emitting red and green light. The filter is going to let through green but not red, and the banana is not producing any blue. So when I put that filter over the banana, we would expect, just by subtractive color mixing, that the banana would look greenish. So I'm going to do that, kind of a desaturated cyan, but now I'll just put it over the banana. And sure enough, you get a greenish banana. Now, what I want to do to illustrate chromatic adaptation is go back to my original image, and instead of putting the cyan filter over just the banana, I'm going to put it over the whole image. And physically, so this goes back to our very first question, is color just physical, or do we need to involve the observer? Physically, the banana is going to be identical to when I just covered the banana, but we'll see what it does perceptually. So here's the filter, here it is just over the banana, and now here it is over the entire image. And I hope what you see is that that banana looks much more yellow now than it does here. And the reason it looks more yellow when I uncover the entire image is because we've adjusted to that overall cyan color cast of the image. We adapt to that. That's chromatic adaptation in our visual system. And relative to that new white point, that banana is yellowish again. And since I have my color meter up, I will indulge you. I don't usually do this, but I'm not worried about cheating. So there you can see this is kind of fun because over here you get to see a sampled version of the color. So that square is green. And you can read the RGB values if you want to. Now, I'm not sure. Let me see if, I'm not going to be able to do this easily. Let me go down here. So I need to click on this first to change the slide there. This should work now. I'll try to change the slide and not move my pointer. Okay, so that works. Pointer's in the exact same place on the 2 images. That banana looks green. This banana looks more yellow, but look up in my little digital color meter window and you can see it's not changing. So just to prove that I'm not cheating, physically that stimulus hasn't changed. Whoops. Physically it hasn't changed, but perceptually it has. And that's tapping to a higher level in your visual system. And that's what we refer to as chromatic adaptation, which is something I've spent a lot of time studying. And basically, The idea is we have these 3 cone responses in our visual system, and they can adjust their sensitivities. And they don't adjust them in unison, they can adjust them independently. So if the lighting is very bluish, we'll be less sensitive to blue light, more sensitive relatively to the red and green, and adjust for that. And
We actually discussed that at the last Mark, at the last color science meeting here in Germany, and some people say it is based on the cones being level equaling out or leveraging out. But who tells the cones what is the right average? So that is something, because we then ask, just imagine just having 3 cones in your retina and having that experiment. So there must be a higher a feedback mechanism telling the cones what is the right ratio. Is there a nice answer to that?
Well, we don't know everything, of course. Some of it happens right within an individual cone. So the light that the cone is sensing, it adapts to that. Now, if that happened exclusively, everything would disappear. The whole world would turn gray. The reason it doesn't is because the cones do not completely adapt to the stimulus, and because we're moving our eyes. So if we think back to my example with the Coke can, my blurring of that image was kind of equivalent to taking a single cone, looking at a point in that image and moving it around and averaging as I moved it around. So that's going on. So the cones are setting their adaptation by averaging over time a little bit. They also integrate over space. So the brain is getting that kind of blurred information. And yes, there is a feedback. There's a feedback to the retina from the brain from that processing. And then at a very much higher level, there are cognitive mechanisms. So recognizable objects will tend to look the color we think they should be. That might help that Coke can demo work so well, because we know we know my banana is yellow.
Yeah, perfect. Okay, let's go again. Good.
I'm going to skip over the details of the modeling here. That's not important for today. The question that we've been looking at, though, is do these individual differences that happen in the absorption of light happen in the adaptation as well? So we've done a fair number of experiments where this is a picture of me again. I'm staring at 2 colors. I remember their appearance under one lighting. This was a simulated daylight. I might switch to a simulate or a real incandescent light and pick from an array of colors what looks like the match. And that's what we call a corresponding colors experiment, to say what stimulus in one viewing condition matches a stimulus in another viewing condition, so we can try to account for the adaptation shifts. So we've done a lot of that. It turns out if we repeat those experiments enough, we can get the precision to a level where we can actually distinguish between different observers. So this is just an example of a green color we were matching from daylight to incandescent light. We had 6 different observers. This is delta, again, delta A star B star plot. The point here is the uncertainty is about the size of this circle. So with enough observations, which happen to be about between 16 and 30 repeats of the experiment for each observer, again, not real practical. You're not going to ask a customer to evaluate an image 30 times before they decide whether it matches or not. But that's what we did to try to see if there were differences. We are able to see those differences. And the other thing I want to point out here is this little blue cross is the average of those 6 observers. This little red star is the prediction from CAD-02, which is the adaptation transform in CCAM-02. It's different than the mean. And within the precision we know, these 2 observers are pretty close to CAD-02. These are fairly far away. Look at these deltas, 10, 15 C-Lab units. So there are significant differences in observers. Part of this is due to metamerism, what we've talked about earlier today. Part of it is due to differences in the adaptation mechanisms. And long story to tell today, but we have been able to separate the 2, and there are individual differences in both cases that might be worth considering. The other little trivial point is we did the experiment where we started in the Luminate A with a test color, made the match under D65 after adapting to D65. Then we used this as the original color and went back to A and made a match to see if the process was reversible. In other words, does alpha equal beta? When we go one way and go back, do we get the same answer? And it turns out if we're precise enough in measuring these, which most times we're not because we don't do these 16 or 30 replications, but when we're precise enough, the answer is no. And this just illustrates, I'll show one here where we start with a green CAT02, CCAM02 would predict you go over here and then back, and our observers went over here somewhere different and back to a different point. So that baffled us. Why are these observers not reversible? And there's a little bit of history of what you saw previously that impacts what you see now. Again, skipping ahead a few more years in the research, while I was locked in my house during the pandemic, I basically moved part of my lab into my basement, and I did experiments on myself and my wife over and over and over again to see if we could measure this in more directly. And we were able to measure a lack of reversibility and adaptation. But in a practical sense, I wouldn't worry about it. It's a fairly small difference. It's a little larger in this experiment because this had some memory effects. In the later experiment, we took away the memory effects, and the difference is still there, but it's not as large. So it's one of those things that's interesting from a vision science standpoint, but from a practical standpoint, nobody should lose any sleep about whether or not going from A to D65 is the same as going from D65 to A. In a practical sense, they are the same.
But practically, to be honest, in the use cases I know here from the printing arena, we typically talk about side-by-side issues. So when people claim about something different or criticize something, they typically have samples, mismatches, seeing at the same time. So it's always side by side. You adapt it to one thing. Yeah. It's nothing. Nobody in my career, people criticize something. You memorize this, and now we go another room, and then see this. Now compared with your memory against this, do you realize the mismatch? And so that's why this chromatic adaptation is, for many things, very, very cool in the background. But when we here in our niche application, we typically are narrow use cases, are side-by-side use cases, and they are challenging enough.
Yeah, that's a good point. In the side-by-side case, the adaptation is mixed somehow. And I don't want to get into the modeling today, but what I've done to model this is actually have the adaptation depend on 3 conditions instead of 1, which is an idea of incomplete adaptation. And one way, just briefly, that could be implemented is there's always a reference point. So that's kind of a constant. The other 2, in your case, could be if they were mismatched, your print and display side by side. And that way you could calculate that mixed adaptation, which has been done and by other people. But yeah, that's absolutely reasonable.
The biggest challenge we have right now, we face here, is that imagine an M1 viewing condition, so with UV, and then have an OBA poor or free reference and an OBA rich print next to it. And the real big question is, when nobody has an answer, just for the gray axis only, forget about colors, but how to move the gray axis from 1 to the what LAB values you have to reproduce on the OBA rich substrate where your paper ends up with 93.1 minus 14 as a true measurement of your M1 condition. But what about the gray axis being consistent with the side-by-side scene reference on the left? And that is something what we study, and we might exchange that because we are doing additional experiments. And we did just a paper or a very small draft report I can share to test. We just made practically different profiles, different mappings, and just compare them by the means of J and Ds in a very rough way. But that still means we don't know the model, and that is something where this is a current question in our graphic arts area.
Yeah.
Okay, we have half an hour, so just to.
Okay, so I don't need to talk about the paper. We just published those results as well. And then moving one level higher up, we're getting to sort of the end of the chain of color vision, is the actual scales of appearance. And that's where I say, if we think back to Moncel now, Moncel described color in terms of lightness, chroma, and hue. He wasn't just using color matching functions. He wasn't using a model of chromatic adaptation. He kind of fixed all of that. He said, you will view my system under certain lighting with a certain background and so on, and actually made the samples. So once you make the samples, the color matching functions really weren't a variable either. But what it was still a variable was the steps. What are the step sizes between the gray levels or between the chroma levels or between the hues? And that's what I mean by scales of appearance. Now we can ask that same question again, are there individual differences? Probably yes, but we're getting to the point where the uncertainty in measuring these things is also larger. So again, if it's not a practical difference for adaptation, it's probably not a practical difference for the scales, but there's a lot more we can learn about the scales. So second poll, Andy, ready?
Yes, yes, 1 second. Okay.
I'll talk while he's setting that up.
Yes, also we wait for feedback. Just talk, go on.
Yep, go ahead. So the question is, what is saturation? And saturation is one of these, well, I won't say what it is until you answer, but it refers to one of these perceptual dimensions. So sometimes we say it's the same thing as chroma, sometimes we say it's similar to chroma, sometimes we use more technical definitions, and I'm curious here, which you're only allowed to pick one, and there is no right answer.
I feel the point changing. It's very fascinating. You know, we have 39% voted, 40% 2, 42, 43. So people are now waking up and pressing the keys. Again, let me wait for it. Now we have 50% voted, 52, so 55. I always try to get my 70%, you know, to close the poll.
We do this in our online classes to see which students turned on their computers more. That's okay.
Yeah, we have 64%, and let me one more. And come on, guys. Okay, I think we leave it with 68%. Okay.
Okay. I like it.
So our audience is kind of educated.
I'm impressed. Very good. I like those answers.
Okay.
So just to review, the only one that I would say is wrong is A. It's not the same thing as chroma. Now that's getting a little technical, but it describes the same dimension. So B is a reasonable answer. It's an attribute similar to chroma. It describes that difference from gray. Technically, the definition is that it's perceived colorfulness relative to perceived brightness of the sample. So if you happen to know your CIE definitions, C is the definition. And it turns out, due to the definitions of chroma and lightness, which are both relative colorfulness relative to the brightness of the white, and brightness relative to the brightness of the white. Sorry, that's a lot of words. D and C are equivalent. And I'm never going to argue with E. It is confusing that we have these multiple words to describe what seems like the same attribute of color appearance, how different something is from neutral. But it turns out they can be useful to have those different words. So, whoops, gotta click back here. So Rod Heckerman and I talked about this a few years ago, and we called deriving appearance scales. And basically what we suggested is maybe we confuse ourselves sometimes by always thinking of three-dimensional color spaces. And then say, let's talk about the C-Lab space. In C-Lab, the dimensions are lightness, chroma, which follows the CIE definition of chroma, and hue. Saturation isn't directly represented in C-Lab. C-star in C-Lab is chroma. Brightness and colorfulness refer to something else that's dealing with our perception of the amount of light in the scene as well. So a given sample, I have my little pink notepad here, if you can see it on the video, that has a certain lightness, chroma, and hue, which we could describe in Munsell or C-Lab. If I turn more lights on in my office here, it will get brighter because there'll be more energy reflecting off of it. And it'll get more colorful because there'll be more energy reflecting off of it. but it'll still be the same object, and I would still describe it with a similar, if not identical, lightness, chroma, and hue, because those are the dimensions that we use to describe the relative appearance. And those are what are useful for materials and objects. To a degree, it eliminates the effect of the lighting. So the way we're thinking about defining these scales better and quantifying the individual differences is what ones are fundamental. And the ones that are fundamental to me, and I'm not saying this is, absolutely correct, but this is the theory we're working out, are brightness, saturation, and hue. Because what we call unrelated colors or light on its own has these attributes. We can think of a light being brighter or darker. We can think of it having a hue. If you think of like street signal lights, the red light and the green light, whether you stop or go, they have a hue, red or green. They have a saturation. They don't look neutral. They look very reddish or very greenish. They're highly saturated. So those attributes can describe any stimulus, whether it's an isolated light or it's a printed object or my sweater or whatever, has a brightness, saturation, and hue. Now, what we're calling secondary terms, or they're for related objects or images, which are a bunch of colors related to each other, that's where the lightness and chroma come in. Because we're saying we aren't so concerned about the overall level of light, we're going to normalize that. Think of the C-Lab calculation. You normalize to the white point, so that always comes out at 100, 0, 0. So those give us lightness and chroma. And then there's this other one, colorfulness, which is related to saturation and brightness, and I'm calling that derivative right now. We may not need colorfulness. That may just be adding to the confusion. And if you remember my poll, the definition of saturation relies on colorfulness. And that's probably why that last choice is so popular, because it tends to confuse things. If we just think of brightness and saturation as fundamental and colorfulness is something derived, maybe it simplifies things. So that's the kind of thing that my student How that I showed in the first image and I are thinking about, is trying to make all of this a little bit less confusing. I'm going to show another slide, which probably will fail at our objective, but maybe you guys can give me some feedback. And this is based on a discussion I had with a couple of my students a week or two ago. And when we finally, after all these years, we're like, what is colorfulness after all? And in scaling it, what we've come to conclude, and this all matches the CIE definitions, by the way. So I'm not saying this is a discovery. This is an attempt to be a teacher and explain it. At constant saturation or constant chromaticity, which happens to be constant perceived saturation, colorfulness is proportional to brightness. So if you have a given, say, RGB values ratio, and you have more or less of it, you're increasing brightness, you're also increasing colorfulness, and saturation stays the same. If you're at constant brightness, colorfulness is proportional to saturation. So the neutral colors, the whites and grays and so on, have no colorfulness or saturation. My red stoplight has a lot of saturation. And then overall, if you take these two proportions, colorfulness is saturation times brightness, which is actually the CIE definition. Saturation is colorfulness relative to brightness. So maybe it would be easier if we had done it this way, to say colorfulness is saturation times how much light you have perceptually, rather than the actual definition, which is the inverse of that. So this is true in theory, and we want it to be literally true in the appearance models. And unfortunately, in appearance models like CCAM02 or CAM16 that are being worked on now, the equations have gotten so complex that it isn't literally true in the mathematics, and that's something we're hoping to repair going forward. And just this note, colorfulness doesn't exist independent of saturation and brightness. It's not an additional dimension. It's a relationship of those dimensions. Now, if that made you only more confused, you can send me a note or whatever, but if it helped, you can send me a note too, because it'd be good to know if that helped. But that's just kind of getting near the end here, the sorts of things that we're thinking about. My boss likes to say, she's the dean of the college, she likes to say, what keeps you up at night? And this is the kind of thing that keeps me up at night, I guess.
I like it.
Other than all the administrative issues. So So a couple of last points here, pretty much to the end, Andy, but I have a few points that you brought up that I'll go on with. This question of brilliance, which is really it's kind of like brightness, and I think it might be the same thing as brightness. This dates back to Ralph Evans, who was at Kodak in the middle of the 20th century. And we think this is the NCS system. Doesn't matter if you're familiar with it or not, but it has an axis kind of like Munsell value over here where the neutrals would be, and it has the maximally chromatic color over here. And what's interesting about this is this edge of the triangle at the top here is the locus that they would call is zero blackness. In the Dean system that we started, the one that Andy sent us, thankfully, that's also here at zero darkness in the system. This is a different hue, but it's along the top. And what we're looking at with brilliance is if we have a constant saturation and we start with black and go up to this axis, it turns out perfect black's down here. We go up to white, we go out to the maximum chromatic color, and we can follow any direction we want. And what happens is if you keep going, if you get up to this axis and then you keep going, you keep adding luminance, the stimuli will start to look like they're glowing. So instead of looking like reflecting objects, they look like lights that are emitting. And there's a line here, Ralph Evans called it G0 for zero grayness, that once you pass that line and you keep adding energy or luminance or brilliance in his terms, you transition from objects, which in the NCS system are here, in the Dean system, they're all on this page, to things that are glowing. And our thought is, if we can define that for all these different saturations, those are really equal brightnesses. If it's not glowing, it's less bright than white. If it is glowing, it's more bright than the diffuse white. And that seems to be working pretty well as a better descriptor of brightness than luminance is, because what happens is this stimulus out here is a much lower luminance than the white, but yet it still looks bright. And that's known as the Helmholtz-Kohlrausch effect, that perceived brightness depends on luminance and chroma, or luminance and colorfulness. And we think looking at these other concepts, we can describe brightness and lightness better. And Andy brought up the question about what do you do when you go beyond an L star of 100 or a lightness of 100? And short answer is I just keep on going, and it's okay. You have a reference point. How you define that reference point, what is L star 100, is very critical. So I work with a lot of people that do high dynamic range displays, televisions, and so on. And that white point, that diffuse white, the thing that looks like it's a piece of paper but not glowing, it turns out it moves all over the place in luminance on the display as you play through a video, just like it does in real life as you walk through real scenes. So figuring that out is difficult. But once you figure that out, that for that moment in time and space is where L star equals 100 is. And then you could have L star values that keep going. And we've done a few experiments. It seems that the scale holds up reasonably well. So if you have a highlight or something and you calculate and it has an L star of 150, that's not a horrible thing. It is outside the normal definition of the system, but it's a reasonable prediction of how our brightness perception carries on beyond that reference point. So it's something we're looking at. It's something that it's gotten a lot of attention lately because of the prevalence of high dynamic range displays. And we all.
And what lazy ADB is reflecting then?
Are they still reflecting? Is that what you said?
No, are they the lazy ADB? Are that the new coordinates you recommend to move to when discussing high dynamic range color differences and color coordinates and visualization?
I would say not yet.
Okay.
There are a few proposals out there. I would, honestly, CLab works fine.
Okay.
We can just I'm not saying we could never do better, but to the degree that we understand this problem, CLab is just fine. All right, and then the other question. Whoops! Every time I get off, there we go. You asked
the whole glowing thing is just about related colors. So It would not make sense to measure that on the moon and find out whether this is self-luminous or reflecting, because depends on the context. Yeah.
Exactly.
Okay.
You need to have some context. So you need a way to set that
Reference.
Yep.
Yeah. Okay.
Yeah,
We have 10 minutes.
The moon is a good one because its reflectance is about 20%. So the moon is actually dark gray, but we never see it that way because we always see it in the sky as an unrelated color. So it looks essentially white.
That's always tricky me when people say there's a dramatic difference between self-luminous objects and reflective objects, and I say normally not. The retina doesn't care, and you have transflective displays where you mostly don't realize the way the photons move typically. So just about context. It's a good example.
Yeah, yeah.
Okay.
So this one last point I have a few more slides that I'll stop after this one though, except for maybe a couple of them.
That is okay. I like the pronunciation. and
Right.
my favorite, again, just to stop, my favorite talk at the CIC, next to, of course, your paper with G0, was Gamut healing. I loved it, the expression. But maybe let's go on, yeah.
So you had asked me when we were talking about this about calculating color differences in different spaces, and we could have weeks of talking about that, but I wanted to make a slide, so I just wrote out the different spaces here, and then I decided there's too much to talk about, so I color coded it. So green means go, red means stop, and I'll explain it. So if you want to calculate color difference between two stimuli, CLAB is the place to do it. That's where all the research has been done. You can use Delta E2000 if you like, but that's still within CLAB.
Yeah.
The reason, so that's green. That's the place to go. The reason I made CCAM02 and CAM16 yellow is because those dimensions aren't as well understood, and they may have some internal inconsistency. So it's a little more questionable what you're measuring there. But there are these versions called CCAM02 UCS and CAM16 UCS, where essentially the idea is combining the concept of Delta E2000 and CLAB with the space. So it's adjusting the space. So I gave them a green with a little bit of yellow. I didn't want to try to get too nuanced in my colors here. So a greenish yellow. If you wanted color differences in those spaces, use the UCS versions because it's accounting for some of the non-uniformity. And then sort of more popular recently, there's ICTCP, which is an encoding space for high dynamic range television, and people like to calculate differences there. There's nothing wrong with calculating differences in the signals, but I would argue they're not colored differences in the sense that they're not perceptual. There's no white point in that space. And until I know what the diffuse white point is, I don't know what color looks like. If I don't know what color looks like, I don't know what the differences between two colors are. So I'm not saying it can't be done, but it's tricky. And that's true in IPT as well, which was it was a space made to have uniform hue lines, not to be uniform for color differences. So nothing says you can't calculate the differences, but the meaning is less and less certain in these than it would be, say, in CLAB. So that's my kind of quick recommendation on that topic. And then we can come back to that if there's questions. I have a little time permitting section that I'm going to skip because I could talk for hours on this. But you may have heard in terms of individual differences that there might be tetrachromatic females out there, and I'll explain why females. It turns out just like color vision deficiencies are a sex-linked trait, and they're carried by females and expressed in males, the possibility to have a fourth cone type or be tetrachromatic is only present in females because of the genetics of how the cone pigments are passed along. I won't get into that today because it's a long explanation. But basically, what can happen is a normal observer has an S, an M, and an L. A normal female actually has two X chromosomes, so she can have two M's and two L's. Normally, they're the same, but it's possible if she's a carrier of a color vision deficiency that she could have S, M, L, and L prime. She could have four different types. And that's where this idea of tetrachromatic females comes from. What's interesting is we kind of know the statistics, and about 12% of females could have this fourth cone type. It's not all the same in all of them. So it's not that it never happens. It happens quite regularly. What's interesting though is, can they use them? And that's this idea of weak versus strong tetrachromacy. Weak means you have 4 kinds of cones. Strong means you actually use them and your color space is 4-dimensional instead of 3-dimensional. And nobody's been found to have this, is the short story. Maybe one in this Jordan et al. Paper in 2010. I won't get into the details, but they found one woman in searching specifically for these that had a slightly different detectability of color differences, but they didn't necessarily show that it was an additional dimension. And my theory here's my example I always use, that this is a 3D color representation of the color checker. Here is a 2D. I've removed 1 dimension of color and then I've gray balanced it on this patch I'm pointing at. So that actually is neutral. You lose a lot of information if you were missing a cone type. My argument is, if there's somebody with 4 dimensions of color perception, 4 strong dimensions, our 3-dimensional reproductions would look this bad to them. They'd look at a television and say, "Oh, it's missing certain colors. It's completely wrong," and that doesn't happen. So that means that at least that these strong tetrachromats aren't common, or they're not complaining for some reason. And the theory is that, yes, they have the 4 types of cones represented here by blue, green, red, and kind of an amber, but they're fed into 3 channels to the brain, so that extra dimension is lost in the wiring. And the reason that would be is that these 2 are very highly correlated for real stimuli out in the world. So since they're really highly correlated, the brain never sees differences among them, and therefore never develops the circuitry to have a 4-dimensional space. And that's probably what's going on, is that we all have really more than 3 sensitivities, because as Andy said, we have 2. Yeah.
Not more spectral differences in the world, which helps us to see more tigers in the background, or more fruits, or more. So that is something, maybe there's no natural benefit, and that's cool hypothesis.
Exactly.
Yeah.
So interesting topic, but I don't think something we really have to worry about, other than if we go back to where I started. The individual color matching functions for a person with 4 cones would be different than, say, what Asano's model predicts, because he never puts a 4th cone in there. So it would change this.
I can share that at the end here, maybe, just to show people some practical stuff here. So just if you see my slide here? Okay, I just added one here. So this is here on that Fogra download and work tools and lighting. You can then go to research results and see that color matching functions to download. And that is the right place here. Again, if you are here, downloads, softproof and lighting, and then you find it here under color matching functions. Cool. It was really a pleasure having you, Mark, and sharing those research. Let me look here in our questions. Okay, whether I can put a link in the chat. Just follow. You go to our downloads, work tools, and then there is softproof and lighting. People are so lazy, they just want the landing page. And then other color matching functions in our Fogra roses, the handbook, and much more cool stuff. So that is okay, Mark. It was a treat having you here. Thanks very much for sharing that. I can share my latest finding with some expert evaluating here this kind of mixed adaptation, OBA rich, OBA poor, down to earth problems here. But it's very cool to see what research is working on and providing the fundamentals for us. Yeah, thank you very much. Let me see whether there's more. 1 second here. Thank you very much. Yeah, there are a lot of people thanking you. There's no question, unfortunately. But now you shared your email, so maybe people are more active in a direct sense. I just saw on the photo as well, Sim is still with you. So give her a hug, please. Yeah. Well, is still in the in the lab?
I'm sorry, I didn't understand the question, Andy.
Is Well still with you in the lab? I saw her on the photo.
Val, she retired
Okay. Okay.
just about a
Okay.
year ago.
So, okay. But okay, if you happen to see her, give her a hug, please. Yeah. Okay.
I do see her once in a while, so I'll let
Okay.
her know.
And for all our attendees, that is not the latest revision here, but you should read that. There's a new 4th revision coming next year, Mark.
Yeah, well,
Okay.
you shouldn't
Sooner or
wait for the third. If you want to read it soon, read the third.
later.
Probably in about 2 years.
Okay, perfect. It's a pleasure. And for those who didn't realize, I'm also wearing here the shortest size. The shortest size I have here is like, the new lab. Yeah, thank you very much, Mark. It was a pleasure. Thank you all for being with us. Have a good time and see you next time. Stay sound and negative.
Thank you.
Bye-bye.
Bye.